Hello, discrete math fans. Let's give an example to illustrate the element method of proof. We'll let C be the set of all integers n, so that n is equal to 6r minus 5 for some integer r. Let's let D be the set of all integers m, such that m is equal to 3s plus 1 for some integer s. And what we'd like to do is prove that C is a subset of D. Alright, the way the element method of proof is supposed to start is we need to select an arbitrary element of the set that we're trying to prove is a subset of the other one. So we're trying to prove that C is a subset of D. That means we need to choose an arbitrary element of C. And that's all that this sentence is really doing. We're saying let n be an element of C. That means it's an arbitrary element of C. Sometimes you will hear people say let n be a random element of C. That's not the right word here. Randomness has connotations of probability in it. We're not doing any probabilistic selection here. This is an arbitrary element of C, which means it could be any element of C. So make sure you don't use the word random element. That's really not the right thing. Alright, so what does it mean for n to be an element of C? It means there exists an integer r such that n is equal to 6r minus 5. Now we want to prove that this n is an element of D. That's our goal. So then we can take n equals 6r minus 5 and rewrite it in such a way so that it looks like 3 times some integer s plus 1. Now, since 2r minus 2 is an integer, we can say that n is an element of D. So that's what we want to prove. We wanted to prove that an arbitrarily chosen element of C is also an element of D. We're not proving that n is equal to C and n is an element of D. What we've proven is that n is an element of C implies that n is an element of D. Very important distinction. Alright, so that concludes the proof here that C is a subset of D. But we're not done. I want to go a little bit further with this. So what I want to do is show, is it possible that D is a subset of C also, going the other direction? Or maybe D is not a subset of C. So let's look to see what the elements of these sets really look like. So C looks like, well, it starts at negative 11, negative 5, 1, 7, 13. I shouldn't say starts there. I mean, doesn't really start anywhere. And then here I've written out a few elements of D. And you can see how all the elements of C really are elements of D, but the other way around looks like is not the case. Looks, for instance, that 4 is an element of D, but 4 is not an element of C. If that's the case, then D will not be a subset of C. Let's prove that 4 is not an element of C. Let's do it with a proof by contradiction. Let's suppose, for the sake of contradiction, that 4 is an element of C. That means that 4 is equal to 6r minus 5 for some integer r, but then if we solve for r, we'll get r equals 3 halves, and that contradicts the fact that r is an element of Z. Therefore, we can conclude that 4 is not an element of C, and this proves, in fact, that D is not a subset of C. Okay, that's all for now.